Aloha from Hawaii. I have to admit I'm kind of an outsider, a newbie to this environment, the OSG. And I think come here through the OSDF NRP path that SDF. And
You're welcome. You're welcome.
thank you. And actually, I want to thank you, Maroon, for invalidating my use of data ubiquitously throughout my presentation slides. So
Okay.
when you say data, you hear object. Okay.
Yeah, okay.
Mouthful, but the highlights really is astronomy. We live in a world in astronomy where we have legitimately big data, petabyte scale, and the historical patterns of data access in astronomy don't scale well. And as a result, with that data. So that's kind of what I want to talk about and how I think this community and especially OSDF gives us a way forward. So here we see the pan stars, and while we can visualize an image of the night sky. This is the 3/4 of the night sky that's actually visible from Hawaii. We have 2 telescopes. Each one has a 1.4 gigapixel camera. About 10 terabytes of image data per night is processed in Hawaii. Okay, it's been running since science operations since 2014. In 2015, we did our initial data release, and that's a 1.6 petabyte data set that's stored at Johns Hopkins in Baltimore and distributed through a NASA archive there. So one was 2015, and that data is piling up in Hawaii. We have over 6 petabytes now of data in Hawaii.
Yeah,
that's right. It's sinking anyway, but we're adding to the weight. So there's a lot of pan stars. In order to continue to get operational funding, shifted from a kind of pure science focus initially to searching for killer asteroids. So Congress has a mandate to NASA to find all the objects that could impact the Earth and cause extinction events. And so Pan-STARRS has been funded since 2017 to find moving objects. So they scan the sky every night, and their funding is to find all the things that move and report them if there's something new, so that other telescopes can determine whether they're on a trajectory that would hit the Earth. That's our bread and butter. And they're not funded to take the scientific results of all of that data together and provide it to the astronomy community. And so we have this kind of silo problem. And then we have other, there we go. We have this is just one, Pan-STARRS is one project. In astronomy, we have ground-based telescopes like Pan-STARRS. There's also space-based satellites that produce data. And then simulation is another source for big data. And Pan-STARRS is a survey, so that means it's a long duration, it runs over years and years every night and produces this nice time series where you're looking at the same objects again and again and again. And we have we have multiple surveys. Another driver for big data in astronomy is Moore's law when it comes to CCDs and imaging. So the camera, 1.4 gigapixel camera, the LSST will have a even larger, I believe 3 gigapixel camera. So there are increases in the instruments of dimensionality and resolution that produce a bigger data stream with every new generation of instruments. And we see that both observing the sun with solar instruments as well as the night sky. Some of the objects, sun, what we call solar system, sun, asteroids, comets, planets, galactic, that means inside the Milky Way galaxy that we belong to, stars, planets around those stars that we call exoplanets, and then extragalactic when we look beyond the Milky Way galaxy at other galaxies and quasars and objects beyond, including cosmology, the universe itself. I'm gonna go back real quick to this. Is there a, yes. Okay, so I want to draw your attention. It's kind of covered by my orange line, but right here is a blob. That's the only visible galaxy, right, in this image. Everything else in this image is inside the galaxy, except that there's about 300 million little tiny dots that actually are galaxies that your eye can't resolve, right? But anyway, so there's, in Pan-STARRS altogether, there are 10 billion separable objects. So their database has 10 billion entries in it, if you will. And it creates search challenges, where you have one list that's 500 million long, and then you're going to match that list to the corresponding object in the 10 billion, right? Which I'm realizing that's a good OSG, OS pool application. DKIST is the world's largest solar telescope. It's located on Maui, on Haleakala at the summit there. Here are some early images, science images from DKIST, showing the extreme high resolution view of the sun's photosphere. So you're looking at convective cells in the surface of the sun and sunspot. Another, it's not super reliable. There we go. I'm part of a team that's doing simulation runs to produce, this is a simulation that corresponds roughly to the picture on the right. And it's chosen specifically to match the results of, I don't know where to point this. So we ran this at Cheyenne, and we have a collection about 50 terabytes with a paper coming out this month that we hope to distribute using OSDF. Canody is a satellite that observes the sun continuously since 2012. So there's, again, a very long time series. This data is archived in Boulder, Colorado by NCAR, High Altitude Observatory. And unfortunately, the efforts to connect with NCAR, I think Brian helped me figure out that this data is actually siloed within NCAR from the climate data. So the work that has been done to include NCAR climate data doesn't quite capture this. But we're hoping to find a way that we can bring this data into OSDF. Randomly pushing this button. I don't know what I'm pointing at. Is there a place I should point to get a better result? Or is it radio?
Should be somewhere in this.
I'll have you do it. Okay. Here's a distribution of some of our surveys. So these are the actual telescope locations on the ground, several in South Africa, several in Chile, Texas, and a bunch in Hawaii that are all different surveys that we operate. You think of time domain astronomy, variable things that change over time. So variable stars that change their brightness, supernovae, where there's a galaxy, and then all of a sudden a bright star appears within that galaxy. It's a big explosion. And then with respect to the sun, solar flares, coronal mass ejections are familiar, but there's other time domain activity. Object classification, a good kind of obvious AI application. And different kinds of regression, like estimating the distance to a galaxy based on observable characteristics of that galaxy that we've done. Weird. Here's an example of what I think is one of the better designed services. So Assassin is another one of our surveys that has a time domain light curve for really any object in the sky. So here you see a query for this particular star, and you want to see how has its brightness changed over time. And so you get that plot. And they have a very nice Python package. They have a very nice load balanced. It's connected to the internet at 10 gig, and they've done a very nice job of trying to create a performant Python API to give their community access to this data, unlike many of the others. And here's another example. So our Atlas survey published a data set of light curves, a static snapshot data set of light curves at that point. And it's at the same NASA archive in Baltimore. Like this data set took me 5 days to download. It's only 29 gigabytes, but the tools create a lot of friction to be able to actually access the data. Oh. And then here's I was referring to the cross matching of 500 million galaxies to 10 billion objects. This is another catalog that we produced that estimates that distance to each galaxy. So there's a bunch of useful science that can be done, but there's a lot of friction and makes it difficult to utilize the data. So that brings me to some of the cyber infrastructure that is available. It's funded through NSF, and it's kind of just a laundry list of different projects, I guess, and different resources that are available to the researcher. And again, my role at the Institute for Astronomy is to help the researchers connect to the resources that are available that are appropriate for the kind of research that they're doing, so that there's not this, we see a lot of grad students that are doing AI on their laptop, and that doesn't scale very well. So trying to match people to the right tools. In bold here were the resources that I particularly have my eye on in terms of which ones I think we can contribute to and use to our benefit. So kind of at a high level, Pelican and OSDF are the middle layer that we can use to researchers could use, whether that's NRP or OS Pool or our own campus HPC and some bespoke resources that we have ourselves. Okay, so I mentioned before, some of the challenges we have are that the NASA archives really were not designed for dealing with the entire sort of population statistic. You don't get to process that 100 terabytes all at once. You do SQL queries against the database back. Typically, researchers don't have robust bandwidth to those archive sites, and the archive sites themselves have limited bandwidth to utilize the data, especially for AI. So some quick examples. You can run a query, but the results of the query have to be a terabyte database. So you just have to iterate and iterate and iterate, and it takes days and days and days. I mentioned I downloaded this 29 gig, it took me 5 days. Here's a paper by a master's student who used Pan-STARRS, the cutout searches. I want to actually download the images, in this case of galaxies, and I want to do some AI application on those galaxies. Well, it took 62 days to download the cutouts for 2 million galaxies. And so he had to do things that he was interested in. Then he had to run for 62 days this process of grabbing a picture of each galaxy. And he had to use the reduced JPEG lossy version of each of those at a reduced over 1,000 days to download the full resolution data set. So these tools just don't scale well. When you use these tools, often there are, please don't use more than 10 threads at a time. So there's throttling limits in place for these tools. Now, there are some projects like LSST where they've so that there are ways to take a flood of data and direct it to the intended users. And there are efforts to provide nice Python packages for querying at these throttling limitations. Okay, so what we're interested in is how to kind of remove these friction points. Kind of the low-hanging fruit is to take bulk data sets and expose them to OSDF through OSDF and Pelican so that they're readily available. The question is, and I guess this is what Maron was pointing out, how do users discover the availability of data, and then how can they access it? So I'm kind of interested in also how we can, if we have a large collection of data in Hawaii, how can we provide a service that runs co-located with the data that allows someone to, in a performant way, query and get the data set that the subset that they're interested in, and expose that as a bucket of objects and inject that into the data caching mechanism in Pelican. And I think what's particularly interesting there would be whether the user can somehow set a lease, an expiration time of the caching. I know that I want to be running my experiment for 100 days. And so I want to extract this data and maybe it's 100 terabytes, and I want to cache it in a way that will persist for 100 days while I run my experiment.
That's the reason why I prefer to talk about staging. Because you're talking about, I want to stage it in OSDF for a certain duration, and I know it's there. But
And I think ideally, it can be, the staging is transparent to the user, but the user might need to declare like what they need. Right?
To a limited extent, because somebody has to manage the space that unfortunately is finite. So that there must be some level of involvement of the end user.
Yeah, the other thing is I think that there's some sweet spot where I can use up the 75 gig that Frank freed up and skip the data staging and actually allow the client to consume the data as a streaming data stream of objects from the data source. So if I have a bunch of data in Hawaii, if I can run a process there that extracts and streams that data into the
I think it's critical, and I'm still I would like to talk to you more about it. Can we identify one small specific use case that like we heard from EHT, that there is a clear customer that wants to do it end to end, and because there are many options, and everything is open, but if we don't have at least one end-to-end example, so if you can work with us on saying, okay, here's one researcher out there that wants to do this, let's see how we get them to benefit, then that would be extremely useful.
I think we have those cases. Anyway, all right. Going to wrap up. I think I've covered the important aspects of this. I'm just going to go. I will mention this. We've got a bunch of data transfer nodes, 4 of them that we deployed in 2018, 1 in Baltimore, 1 in Tokyo, 2 in Hawaii. We're updating some of those and plan to convert them into data origins. And I'm curious to find out whether you can run a data cache as well as a data origin on the same hardware platform. Given the separation in Pelican, it seems like maybe that's a possibility, because I think these could be used in both roles. And so I think this is an area that we're definitely working on. Yeah, and so then at the end of my slides are a set of resource links, and that's it. If you're interested in any of this, feel free to contact me by email.